and are able to build some of your own data pipelines, you're ready to learn some more advanced techniques that allow you to build more complex cases involving external systems, custom components, and more. In Chapter 6, we'll examine how you can trigger pipelines in ways that don't involve fixed schedules. This allows you to trigger pipelines in response to certain events, such as new files coming in or a call from an HTTP service. Chapter 7 will demonstrate how to use Airflow's built-in functionality to run tasks on external systems. This is an extremely powerful feature of Airflow that allows you to build pipelines that coordinate data flows across many different systems, such as databases, computational frameworks such as Apache Spark, and storage systems. Next, Chapter 8 will show you how you can build custom components for Airflow, allowing you to execute tasks on systems not supported by Airflow's built-in functionality. This functionality can also be used to build components that can easily be reused across your pipelines to support common workflows. To help increase the robustness of your pipelines, Chapter 9 elaborates on different strategies you can use to test your data pipelines and custom components. This has been a commonly recurring topic in Airflow meetups, so we'll spend some time exploring it. Finally, Chapter 10 dives into using container-based approaches for implementing tasks in your pipelines. We'll show you how you can run tasks using both Docker and Kubernetes, and discuss several advantages and drawbacks of using containers for your tasks. After completing Part 2, you should be well underway to becoming an advanced Airflow user, being able to write complex and testable pipelines that optionally involve custom components and/or containers. However, depending on your interests, you may want to pick specific chapters to focus on, as not all chapters may be relevant to your use case. Chapter 6: Triggering Workflows. This chapter covers waiting for certain conditions to be met with sensors, deciding how to set dependencies between tasks in different DAGs, executing workflows via the CLI and REST API. In Chapter 3, we explored how to schedule workflows in Airflow based on a time interval. The time intervals can be given as convenience strings, for example, @daily, time delta objects, for example, time delta days equals 3, or cron strings, for example, 30, 14, star, star, star. These are all notations to instruct the workflow to trigger at a certain time or interval. Airflow will compute the next time to run the workflow given the interval, and start the first task or tasks in the workflow at the next date and time. In this chapter, we explore other ways to trigger workflows. This is often desired following a certain action, in contrast to the time-based intervals, which start workflows at predefined times. Trigger actions are often the result of external events. Think of a file being uploaded to a shared drive, a developer pushing their code to a repository, or the existence of a partition in a Hive table, any of which could be a reason to start running your workflow. Section 6.1: Polling conditions with sensors. One common use case to start a workflow is the arrival of new data. Imagine a third party delivering a daily dump of its data on a shared storage system between your company and the third party. Assume we're developing a popular mobile couponing app and are in contact with all supermarket brands to deliver a daily export of their promotions that are going to be displayed in our couponing app. Currently, the promotions are mostly a manual process. Most supermarkets employ pricing analysts to take many factors into account and deliver accurate promotions. Some promotions are well thought out weeks in advance, and some are spontaneous one-day flash sales. The pricing analysts carefully study competitors, and sometimes promotions are made late at night. Hence, the daily promotions data often arrives at random times. We saw data arrive on the shared storage between 1600 and 2 o'clock the next day, although the daily data can be delivered at any time of the day. Let's develop the initial logic for such a workflow. Figure 6.1. In this workflow, we copy the supermarket's 1 to 4 delivered data into our own raw storage from which we can always reproduce results. The process_supermarket_1, 2, 3, 4 tasks then transform and store all raw data in a results database that can be read by the app. And finally, the create_metrics task computes and aggregates several metrics that give insights in the promotions for further analysis. With data from the supermarkets arriving at varying times, the timeline of this workflow could look like figure 6.2. Here we see the data delivery times of the supermarkets and the start time of our workflow. Since we've experienced supermarkets delivering data as late as 2, a safe bet would be to start the workflow at 2 to be certain all supermarkets have delivered their data. However, this results in lots of waiting time. Supermarket 1 delivered its data at 16:30, while the workflow starts processing at 2 but does nothing for 9.5 hours, figure 6.3. One way to solve this in Airflow is with the help of sensors, which are a special type, subclass of operators. Sensors continuously poll for certain conditions to be true and succeed if so. If false, the sensor will wait and try again until either the condition is true or a timeout is eventually reached. This file sensor will check for the existence of /data/supermarket1/data.csv and return true if the file exists. If not, it returns false, and the sensor will wait for a given period, default 60 seconds, and try again. Both operators, sensors are also operators, and DAGs have configurable timeouts, and the sensor will continue checking the condition until a timeout is reached. We can inspect the output of sensors in the task logs. Here we see that approximately once a minute, the sensor pokes for the availability of the given file. Poking is Airflow's name for running the sensor and checking the sensor condition. Footnote 1. Configurable with the poke_interval argument. When incorporating sensors into this workflow, one change should be made. Now that we know we won't wait until 2 and assume all data is available, but instead start continuously checking if the data is available, the DAG start time should be placed at the start of the data arrival boundaries, figure 6.4. The corresponding DAG will have a task, file sensor, added to the start of processing each supermarket's data and would look like figure 6.5. In figure 6.5, sensors were added at the start of the DAG, and the DAG's schedule_interval was set to start before the expected delivery of data. This way, sensors at the start of the DAG would continuously poll for the availability of data and continue to the next task once the condition has been met, that is, once the data is available in the given path. Here we see Supermarket 1 has already delivered data, which sets the state of its corresponding sensor to success, and continues processing its downstream tasks. As a result, data was processed directly after delivery, without unnecessarily waiting until the end of the expected time of delivery. Section 6.1.1, Polling Custom Conditions. Some datasets are large and consist of multiple files, that is, data-01.csv, data-02.csv, data-03.csv, etc. Airflow's file sensor supports wildcards to match, for example, data-star.csv, which will match any file matching the pattern. So if, for example, the first file, data-01.csv, is delivered while others are still being uploaded to the shared storage by the supermarket, the file sensor would return true, and the workflow would continue to the copy_to_raw task, which is undesirable. Therefore, we agree with the supermarkets to write a file named _success as the last part of uploading, to indicate the full daily data set was uploaded. The data team decided they want to check for both the existence of one or more files named data-star.csv and one file named _success. Under the hood, the file sensor uses globbing. See this link, to match patterns against file or directory names. While globbing, similar to regex but more limited in functionality, would be able to match multiple patterns with a complex pattern, a more readable approach is to implement the two checks with the Python sensor. The Python sensor is similar to the Python operator in the sense that you supply a Python callable, function, method, etc., to execute. However, The Python sensor callable is limited to returning a Boolean value, true to indicate the condition is met successfully, false to indicate it is not. Let's check out a Python sensor callable checking these two conditions. The callable supplied to the Python sensor is executed and expected to return a Boolean true or false. The callable shown in listing 6.2 now checks two conditions, namely if both the data and the success file exist. Other than using a different color, the Python sensor tasks appear the same in the UI, figure 6.6. Section 6.1.2, Sensors outside the happy flow. Now that we've seen sensors running successfully, what happens if a supermarket one day doesn't deliver its data? By default, sensors will fail just like operators, figure 6.7. Sensors accept a timeout argument, which holds the maximum number of seconds a sensor is allowed to run. If at the start of the next poke, the number of running seconds turns out to be higher than the number set to timeout, the sensor will fail. By default, the sensor timeout is set to 7 days. If the DAG schedule_interval is set to once a day, this will lead to an undesired snowball effect, which is surprisingly easy to encounter with many DAGs. The DAG runs once a day, and supermarkets 2, 3, and 4 will fail after 7 days, as shown in figure 6.7. However, new DAG runs are added every day, and the sensors for those respective days are started. And as a result, more and more tasks start running. Here's the catch. There's a limit to the number of tasks Airflow can handle and will run on various levels. It is important to understand there are limits to the maximum number of running tasks on various levels in Airflow. The number of tasks per DAG, the number of tasks on a global Airflow level, the number of DAG runs per DAG, and so on. In figure 6.8, we see 16 running tasks, which are all sensors. The DAG class has a concurrency argument, which controls how many simultaneously running tasks are allowed within that DAG. In figure 6.8, we ran the DAG with all defaults, which is 16 concurrent tasks per DAG. The following snowball effect happened. Day 1. Supermarket 1 succeeded. Supermarkets 2, 3, and 4 are polling, occupying 3 tasks. Day 2. Supermarket 1 succeeded. Supermarkets 2, 3, and 4 are polling, occupying 6 tasks. Day 3. Supermarket 1 succeeded. Supermarkets 2, 3, and 4 are polling, occupying 9 tasks. Day 4. Supermarket 1 succeeded. Supermarkets 2, 3, and 4 are polling, occupying 12 tasks. Day 5. Supermarket 1 succeeded. Supermarkets 2, 3, and 4 are polling, occupying 15 tasks. Day 6. Supermarket 1 succeeded. Supermarkets 2, 3, and 4 are polling, occupying 16 tasks. 2 new tasks cannot run, and any other task trying to run is blocked. This behavior is often referred to as sensor deadlock. In this example, the maximum number of running tasks in the supermarket couponing DAG is reached, and thus the impact is limited to that DAG, while other DAGs can still run. However, once the global Airflow limit of maximum tasks is reached, your entire system is stalled, which is obviously undesirable. This issue can be solved in various ways. The sensor class takes an argument, mode, which can be set to either poke or reschedule, available since Airflow 1.10.2. By default, it's set to poke, leading to the blocking behavior. This means the sensor task occupies a task slot as long as it's running. Once in a while, it pokes the condition and then does nothing, but still occupies a task slot. The sensor reschedule mode releases the slot after it has finished poking, so it only occupies a slot while it's doing actual work. Figure 6.9. The number of concurrent tasks can also be controlled by several configuration options on the global Airflow level, which are covered in section 12.6. In the next section, let's look at how to split up a single DAG into multiple smaller DAGs, which trigger each other to separate concerns. Section 6.2, Triggering Other DAGs. At some point in time, more supermarkets are added to our couponing service. More and more people would like to gain insights in the supermarket's promotions, and the create_metrics step at the end is executed only once a day, after all supermarkets' data was delivered and processed. In the current setup, it depends on the successful state of the process_supermarket_1, 2, 3, 4 tasks, figure 6.10. We received a question from the analyst team about if the metrics could also be made available directly after processing, instead of having to wait for other supermarkets to deliver their data and run it through the pipeline. We have several options here, depending on the logic it performs. We could set the create_metrics task as a downstream task after every process_supermarket_star task, figure 6.11. Suppose the create_metrics task evolved into multiple tasks, making the DAG structure more complex and resulting in more repeated tasks, figure 6.12. One option to circumvent repeated tasks with almost equal functionality is to split your DAG into multiple smaller DAGs, where each takes care of a part of the total workflow. One benefit is you can call DAG2 multiple times from DAG1, instead of one single DAG holding multiple duplicated tasks from DAG2. Whether this is possible or desirable depends on many things, such as the complexity of the workflow. If, for example, you'd like to be able to create the metrics without having to wait for the workflow to complete according to its schedule, but instead trigger it manually whenever you'd like, then it could make sense to split it into two separate DAGs. This scenario can be achieved with the trigger DAG run operator. This operator allows triggering other DAGs, which you could apply to decouple parts of a workflow. The string provided to the trigger_DAG_ID argument of the trigger DAG run operator must match the DAG_ID of the DAG to trigger. The end result is that we now have two DAGs, one for ingesting data from the supermarkets and one for computing metrics on the data, figure 6.13. Visually, in the Airflow UI, there is almost no difference between a scheduled DAG, manually triggered DAG, or an automatically triggered DAG. Two small details in the tree view tell you whether a DAG was triggered or started by a schedule. First, scheduled DAG runs and their task instances show a black border, figure 6.14. Second, each DAG run holds a field, run_ID. The value of the run_ID starts with one of the following. Scheduled_ to indicate the DAG run started because of its schedule. Backfill_ to indicate the DAG run started by a backfill job. Manual_ to indicate the DAG run started by a manual action, for example, pressing the trigger DAG button, or triggered by a trigger DAG run operator. Hovering over the DAG run circle displays a tooltip showing the run_ID value, telling us how the DAG started running, figure 6.15. Section 6.2.1, Backfilling with the trigger DAG run operator. What if you changed some logic in the process_star tasks and wanted to rerun the DAGs from there on? In a single DAG, you could clear the state of the process_star and corresponding downstream tasks. However, clearing tasks only clears tasks within the same DAG. Tasks downstream of a trigger DAG run operator in another DAG are not cleared, so be well aware of this behavior. Clearing tasks in a DAG, including a trigger DAG run operator, will trigger a new DAG run instead of clearing the corresponding previously triggered DAG runs, figure 6.16. Section 6.2.2, Polling the state of other DAGs. The example in figure 6.13 works as long as there is no dependency from the to-be-triggered DAGs back to the triggering DAG. In other words, the first DAG can trigger the downstream DAG whenever, without having to check any conditions. If the DAGs become very complex, for clarity, the first DAG could be split across multiple DAGs, and a corresponding trigger DAG run operator task could be made for each corresponding DAG, as seen in figure 6.17 in the middle. Also, one DAG triggering multiple downstream DAGs is a possible scenario with the trigger DAG run operator, as seen in figure 6.17 on the right. But what if multiple triggering DAGs must complete before another DAG can start running? For example, what if DAGs 1, 2, and 3 each extract, transform, and load a dataset, and you'd like to run DAG 4 only once all 3 DAGs have been completed, for example, to compute a set of aggregated metrics? Airflow manages dependencies between tasks within one single DAG. However, it does not provide a mechanism for inter-DAG dependencies. Figure 6.18. Footnote 2. This Airflow plugin visualizes inter-DAG dependencies by scanning all your DAGs for usage of the trigger DAG run operator and external task sensor. See this link. For this situation, we could apply the external task sensor, which is a sensor poking the state of tasks in other DAGs, as shown in figure 6.19. This way, the wait_for_etl_DAG 1, 2, 3 tasks act as a proxy to ensure the completed state of all 3 DAGs before finally executing the report task. The way the external task sensor works is by pointing it to a task in another DAG to check its state. Figure 6.20. Since there is no event from DAG 1 to DAG 2, DAG 2 is polling for the state of a task in DAG 1. But this comes with several downsides. In Airflow's world, DAGs have no notion of other DAGs. While it's technically possible to query the underlying metastore, which is what the external task sensor does, or read DAG scripts from disk and infer the execution details of other workflows, they are not coupled in Airflow in any way. This requires a bit of alignment between DAGs in case the external task sensor is used. The default behavior is such that the external task sensor simply checks for a successful state of a task with the exact same execution date as itself. So, if an external task sensor runs with an execution date of 2019-10-12-T-18-0000, it would query the Airflow metastore for the given task, also with an execution date of 2019-10-12-T-18-0000. Now let's say both DAGs have a different schedule interval. Then these would not align, and thus the external task sensor would never find the corresponding task. See figure 6.21. In case the schedule intervals do not align, we can offset, by which the external task sensor must search for the task in the other DAG. This offset is controlled by the execution_delta argument on the external task sensor. It expects a time delta object, and it's important to know it operates counterintuitive from what you expect. The given time delta is subtracted from the execution_date, meaning that a positive time delta actually looks back in time. Figure 6.22. Note that checking a task using the external task sensor where the other DAG has a different interval period, for example, DAG 1 runs once a day and DAG 2 runs every 5 hours, complicates setting a good value for execution_delta. For this use case, it's possible to provide a function returning a list of time deltas via the execution_date_fn argument. Refer to the Airflow documentation for the details. Section 6.3. Starting workflows with REST CLI. In addition to triggering DAGs from other DAGs, they can also be triggered via the REST API and CLI. This can be useful if you want to start workflows from outside Airflow, for example, as part of a CI/CD pipeline, or data arriving at random times in an AWS S3 bucket can be processed by setting a Lambda function to call the REST API, triggering a DAG instead of having to run sensors polling all the time. Using the Airflow CLI, we can trigger a DAG as follows. This triggers DAG 1 with the execution date set to the current date and time. The DAG run ID is prefixed with manual_ to indicate it was triggered manually or from outside Airflow. The CLI accepts additional configuration to the triggered DAG. This piece of configuration is then available in all tasks of the triggered DAG run via the task context variables. These tasks print the conf provided to the DAG run, which can be applied as a variable throughout the task. As a result, if you have a DAG in which you run copies of tasks simply to support different variables, this becomes a whole lot more concise with the DAG run conf, since it allows you to insert variables into the pipeline, figure 6.23. However, note that the DAG in listing 6.8 has no schedule interval, that is, it only runs when triggered. If the logic in your DAG relies on a DAG run conf, then it won't be possible to run on a schedule, since that doesn't provide any DAG run conf. Similarly, it is also possible to use the REST API for the same result. For example, in case you have no access to the CLI, but your Airflow instance can be reached over HTTP. This could be convenient when triggering DAG from outside Airflow, for example, from your CI/CD system. Summary. Sensors are a special type of operators that continuously poll for a given condition to be true. Airflow provides a collection of sensors for various systems, use cases. A custom condition can also be made with the Python sensor. The trigger DAG run operator can trigger a DAG from another DAG, while the external task sensor can poll the state in another DAG. Triggering DAGs is possible from outside Airflow with the REST API and/or CLI. Chapter 7. Communicating with External System. This chapter covers working with Airflow operators performing actions on systems outside Airflow, applying operators specific to external systems, implementing operators in Airflow doing A to B operations, testing tasks connecting to external systems. In all previous chapters, we've focused on various aspects of writing Airflow code, mostly demonstrated with examples using generic operators, such as the bash operator and Python operator. While these operators can run arbitrary code, and thus could run any workload, the Airflow project also holds other operators for more specific use cases. For example, running a query on a Postgres database. These operators have one and only one specific use case, such as running a query. As a result, they are easy to use by simply providing the query to the operator, and the operator internally handles the querying logic. With a Python operator, you would have to write such querying logic yourself. For the record, with a phrase external system, we mean any technology other than Airflow and the machine Airflow is running on. This could be, for example, Microsoft Azure Blob Storage, an Apache Spark cluster, or a Google BigQuery data warehouse. To see when and how to use such operators, in this chapter we'll develop two DAGs connecting two external systems and moving and transforming data between these systems. We will inspect the various options Airflow holds, and does not hold, to deal with this use case and the external systems. Footnote 1. Operators are always under development. This chapter was written in 2020. Please note at the time of reading there might be new operators that suit your use case that were not described in this chapter. In section 7.1, we develop a machine learning model on AWS, working with AWS S3 buckets and AWS SageMaker, a solution for developing and deploying machine learning models. Next, in section 7.2, we demonstrate how to move data between various systems with a Postgres database containing Airbnb places to stay in Amsterdam. The data comes from inside Airbnb. See this link. A website and public data managed by Airbnb, with records about listings, reviews, and more. Once a day, we will download the latest data from the Postgres database into our AWS S3 bucket. From there, we will run a pandas job inside a Docker container to determine the price fluctuations, and the result is saved back to S3. Section 7.1. Connecting to Cloud Services. A large portion of software runs on cloud services nowadays. Such services can generally be controlled via an API, an interface to connect and send requests to your cloud provider. The API typically comes with a client in the form of a Python package. For example, AWS's client is named BOTO3. See this link. GCP's client is named the Cloud SDK. See this link. and Azure's client is appropriately named the Azure SDK for Python. See this link. Such clients provide convenient functions where, bluntly said, you enter the required details for a request, and the clients handle the technical internals of handling the request and response. In the context of Airflow, to the programmer, the interface is an operator. Operators are the convenience classes to which you can provide the required details to make a request to a cloud service, and the operator internally handles the technical implementation. These operators internally make use of the Cloud SDK to send requests and provide a small layer around the Cloud SDK, which provides certain functionality to the programmer. Figure 7.1. Section 7.1.1. Installing extra dependencies. The Apache Airflow Python package includes a few essential operators, but no components to connect with any cloud. For the cloud services, you can install the provider packages in Table 7.1. This goes not only for the cloud providers, but also for other external services. For example, to install operators and corresponding dependencies required for running the Postgres operator, install the Apache Airflow Providers Postgres package. For a full list of all available additional packages, refer to the Airflow documentation at this link. Let's look at an operator to perform an action on AWS. Take, for example, the S3 copy object operator. This operator copies an object from one bucket to another. It accepts several arguments, skipping the irrelevant arguments for this example. This operator makes copying an object on S3 to a different location on S3 a simple exercise of filling in the blanks, without needing to dive into the details of AWS's BOTO3 client. Footnote 2. If you check the implementation of the operator, internally it calls copy_object on BOTO3. Section 7.1.2. Developing a machine learning model. Let's look at a more complex example and work with a number of AWS operators by developing a data pipeline building a handwritten numbers classifier. The model will be trained on the MNIST, see this link, dataset, containing approximately 70,000 handwritten digits 0 to 9, figure 7.2. After training the model, we should be able to feed it a new, previously unseen handwritten number, and the model should classify the handwritten number, figure 7.3. There are two parts to the model, an offline and an online part. The offline part takes a large set of handwritten digits, trains a model to classify these handwritten digits, and the result, a set of model parameters, is stored. This process can be done periodically when new data is collected. The online part is responsible for loading the model and classifying previously unseen digits. This should run instantaneously, as users expect direct feedback. Airflow workflows are typically responsible for the offline part of a model. Training a model comprises data loading, pre-processing it into a format suitable for the model, and training the model, which can become complex. Also, periodically retraining the model fits nicely with Airflow's batch processing paradigm. The online part is typically an API, such as a REST API or HTML page with REST API calls under the hood. Such an API is typically deployed only once or as part of a CI/CD pipeline. There is no use case for redeploying an API every week, and therefore it's typically not part of an Airflow workflow. For training a handwritten digit classifier, we'll develop an Airflow pipeline. The pipeline will use AWS SageMaker, an AWS service facilitating the development and deployment of machine learning models. In the pipeline, we first copy sample data from a public location to our own S3 bucket. Next, we transform the data into a format usable for the model, train the model with AWS SageMaker, and finally, deploy the model to classify a given handwritten digit. The pipeline will look like figure 7.4. The depicted pipeline could run just once, and the SageMaker model could be deployed just once. The strength of Airflow is the ability to schedule such a pipeline and rerun partial pipelines if desired in case of new data or changes to the model. If the raw data is continuously updated, the Airflow pipeline will periodically reload the raw data and redeploy the model, trained on the new data. Also, a data scientist could tune the model to their liking, and the Airflow pipeline could automatically redeploy the model without having to manually trigger anything. Airflow holds several operators on various services of the AWS platform. While the list is never complete because services are continuously added, changed, or removed, most AWS services are supported by an Airflow operator. AWS operators are provided by the Apache-Airflow-Providers-Amazon package. Let's look at the pipeline, figure 7.5. Even though there are just 4 tasks, there's quite a lot to configure on AWS SageMaker, and hence the DAG code is lengthy. No worries though, we'll break it down afterward. With external services, the complexity often does not lie within Airflow, but with ensuring the correct integration of various components in your pipeline. There's quite a lot of configuration involved with SageMaker, so let's break down the tasks piece by piece. After initializing the DAG, the first task copies the mnist dataset from a public bucket to our own bucket. We store it in our own bucket for further processing. The S3 copy object operator asks for both the bucket and object name on the source and destination, and will copy the selected object for you. So, while developing, how do we verify this works correctly without first coding the full pipeline and keeping fingers crossed to see if it works in production? Section 7.1.3. Developing locally with external systems. Specifically for AWS, if you have access to the cloud resources from your development machine with an access key, you can run Airflow tasks locally. With the help of the CLI command, Airflow tasks test, we can run a single task for a given execution date. Since the download_mnist_data task doesn't use the execution date, it doesn't matter what value we provide. However, say the dest_bucket_key was given as mnist-ds_pkl.gz. Then we'd have to think wisely about what execution date we test with. From your command line, complete the steps in the following listing. This will run the task download_mnist_data and display logs. After this, we can see the data was copied into our own bucket, figure 7.6. What just happened? We configured the AWS credentials to allow us to access the cloud resources from our local machine. While this is specific to AWS, similar authentication methods apply to GCP and Azure. The AWS BOTO3 client used internally in Airflow operators will search in various places for credentials on the machine where a task is run. In listing 7.4, we see the AWS_profile environment variable, which the BOTO3 client picks up for authentication. After this, we set another environment variable, Airflow_home. This is the location where Airflow will store logs and such. Inside this directory, Airflow will search for a /dags directory. If that happens to live elsewhere, you can point Airflow there with another environment variable, Airflow_core_dags_folder. Next, we run Airflow DB init. Before doing this, ensure you either have not set Airflow_core_SQL_alchemy_con, a URI that points to a database for storing all state, or set it to a database URI specifically for testing purposes. Without Airflow_core_SQL_alchemy_con set, Airflow DB init initializes a local SQLite database, a single file, no configuration required, database, inside Airflow_home. Airflow tasks test exists for running and verifying a single task and does not record any state in the database. However, it does require a database for storing logs, and therefore we must initialize one with Airflow DB init. Footnote 3. The database will be generated in a file name airflow.db in the directory set by Airflow_home. You can open and inspect it with, for example, dbeaver. After all this, we can run the task from the command line with Airflow tasks test chapter 7 _AWS _handwritten _digits _classifier extract _mnist _data 2020-01-01. After we've copied the file to our own S3 bucket, we need to transform it into a format the SageMaker k-means model expects, which is the record IO format. Footnote 4. MIME type application/x-recordio-protobuf documentation. See this link. Airflow in itself is a general-purpose orchestration framework with a manageable set of features to learn. However, working in the data field often takes time and experience to know about all technologies and to know which dots to connect in which way. You never develop Airflow alone. Oftentimes you're connecting to other systems and reading the documentation for that specific system. While Airflow will trigger the job for such a task, the difficulty in developing a data pipeline often lies outside Airflow and with the system that you're communicating with. While this book focuses solely on Airflow, due to the nature of working with other data processing tools, we try to demonstrate via these examples what it's like to develop a data pipeline. For this task, there is no existing functionality in Airflow for downloading data and extracting, transforming, and uploading the result back to S3. Therefore, we must implement our own function. The function downloads the data into an in-memory binary stream, io.bytes.io, so that the data is never stored in a file on the file system, and so that no remaining files are left after the task. The MNIST dataset is small, 15 megabytes, and will therefore run on any machine. However, think wisely about the implementation. For larger data, it might be wise to opt for storing the data on disks and processing in chunks. Similarly, this task can also be run, tested, locally with. Once completed, the data will be visible in S3, figure 7.7. The next two tasks train and deploy the SageMaker model. The SageMaker operators take a config argument, which entails configuration specific to SageMaker and is not in the scope of this book. Let's focus on the other arguments. Many of the details in config are specific to SageMaker and can be discovered by reading the SageMaker documentation. 2 lessons applicable to working with any external system can be made, though. First, AWS restricts the training job name to be unique within an AWS account and region. Running this operator with the same training job name twice will return an error. Say we provided a fixed value, MNIST classifier, to the training job name. Running it a second time would result in failure. The config argument can be templated, and hence, if you plan to retrain your model periodically, you must provide it a unique training job name, which we can do by templating it with the execution_date. This way, we ensure our task is idempotent and existing training jobs do not result in conflicting names. Second, note the arguments wait_for_completion and check_interval. If wait_for_completion were set to false, the command would simply fire and forget. That's how the BOTO3 client works. AWS would start a training job, but we'd never know if the training job completed successfully. Therefore, all SageMaker operators wait. Default wait_for_completion equals true for the given task to complete. Internally, the operators poll every X seconds, checking to see if the job is still running. This ensures our Airflow tasks only complete once finished, figure 7.8. If you have downstream tasks and want to ensure the correct behavior and order of your pipeline, you'll want to wait for completion. Once the full pipeline is complete, we have successfully deployed a SageMaker model and endpoint to expose it, figure 7.9. However, in AWS, a SageMaker endpoint is not exposed to the outside world. It is accessible via the AWS APIs, but not, for example, via a worldwide accessible HTTP endpoint. Of course, to complete the data pipeline, we'd like to have a nice interface or API to feed handwritten digits and receive a result. In AWS, in order to make it accessible to the internet, we could deploy a Lambda, such as this, to trigger the SageMaker endpoint, and an API gateway, such as this, to create an HTTP endpoint, forwarding requests to the Lambda, so why not integrate them into our pipeline? Figure 7.10. Footnote 5. Chalice, see this link, is a Python framework similar to Flask for developing an API and automatically generating the underlying API gateway and Lambda resources in AWS. The reason for not deploying infrastructure is the fact the Lambda and API gateway will be deployed as one-offs, not periodically. They operate in the online stage of the model and therefore are better deployed as part of a CI/CD pipeline. For the sake of completeness, the API can be implemented with Chalice. The API holds one single endpoint, which accepts a JPEG image. The result, if trained correctly, looks like figure 7.11. The API transforms the given image into record I/O format, just like the SageMaker model was trained on. The record I/O object is then forwarded to the SageMaker endpoint deployed by the Airflow pipeline, and finally returns a prediction for the given image. Section 7.2. Moving data from between systems. A classic use case for Airflow is a periodic ETL job where data is downloaded daily and transformed elsewhere. Such a job is often for analytical purposes, where data is exported from a production database and stored elsewhere for processing later. The production database is most often, depending on the data model, not capable of returning historical data. For example, the state of the database as it was 1 month ago. Therefore, a periodic export is often created and stored for later processing. Historic data dumps will grow your storage requirements quickly and require distributed processing to crunch all data. In this section, we'll explore how to orchestrate such a task with Airflow. We've developed a GitHub repository with code examples to go along with this book. It contains a Docker Compose file for deploying and running the next use case, where we extract Airbnb listings data and process it in a Docker container with pandas. In a large-scale data processing job, the Docker container could be replaced by a Spark job, which distributes the work over multiple machines. The Docker Compose file contains the following: one Postgres container holding the Airbnb Amsterdam listings, one AWS S3 API compatible container. Since there is no AWS S3 in Docker, we created a MINIO container, AWS S3 API compatible object storage, for reading, writing data. One Airflow container. Visually, the flow will look like figure 7.12. Airflow acts as the spider in the web, starting and managing jobs and ensuring all finish successfully in the correct order, failing the pipeline if not. The Postgres container is a custom-built Postgres image holding a database filled with inside Airbnb data available on Docker Hub as Airflow Book inside Airbnb. The database holds one single table named Listings, which contains records of places in Amsterdam listed on Airbnb between April 2015 and December 2019, figure 7.13. Let's first query the database and export data to S3. From there, we will read and process the data with pandas. A common task in Airflow is a data transfer between two systems, possibly with a transformation in between. Querying a MySQL database and storing the result on Google Cloud Storage, copying data from an SFTP server to your data lake on AWS S3, or calling an HTTP REST API and storing the output have one thing in common, namely that they deal with two systems, one for the input and one for the output. In the Airflow ecosystem, this has led to the development of many such A to B operators. For these examples, we have the MySQL to Google Cloud Storage operator, SFTP to S3 operator, and the simple HTTP operator. While there are many use cases to cover with the operators in the Airflow ecosystem, there is no Postgres query to AWS S3 operator at the time of writing this book. So, what to do? Section 7.2.1. Implementing a Postgres to S3 operator. First, we could take note of how other similar operators work and develop our own Postgres to S3 operator. Let's look at an operator closely related to our use case. The Mongo to S3 operator in airflow.providers.amazon.aws.transfers.mongo_to_S3 after installing Apache Airflow Providers Amazon. This operator runs a query on a MongoDB database and stores the result in an AWS S3 bucket. Let's inspect it and figure out how to replace MongoDB with Postgres. The execute method is implemented as follows. Some code was obfuscated. It's important to note that this operator does not use any of the file systems on the Airflow machine, but keeps all results in memory. The flow is basically... Since this operator keeps the intermediate results in memory, think wisely about the memory implications when running very large queries, because a very large result could potentially drain the available memory on the Airflow machine. For now, let's keep the Mongo to S3 operator implementation in mind and look at one other A to B operator, the S3 to SFTP operator. This operator, again, instantiates two hooks, SSH hook. SFTP is FTP over SSH, and S3 hook. However, in this operator, the intermediate result is written to a named temporary file, which is a temporary place on the local file system of the Airflow instance. In this situation, we do not keep the entire result in memory, but we must ensure enough disk space is available. Both operators have two hooks in common, one for communicating with system A and one for communicating with system B. However, how data is retrieved and transferred between systems A and B is different, and up to the person implementing the specific operator. In the specific case of Postgres, database cursors can iterate to fetch and upload chunks of results. However, this implementation detail is not in the scope of this book. Keep it simple and assume the intermediate result fits within the resource boundaries of the Airflow instance. A very minimal implementation of a Postgres to S3 operator could look as follows. Let's inspect this code. The initialization of both hooks is straightforward. We initialize them, providing the name of the connection ID the user provides. While it is not necessary to use keyword arguments, you might notice the S3 hook takes the argument AWS_con_ID and not S3_con_ID as you might expect. During the development of such an operator and the usage of such hooks, it is inevitable to sometimes dive into the source code or carefully read the documentation to view all available arguments and understand how things are propagated into classes. In the case of the S3 hook, it subclasses the AWS hook and inherits several methods and attributes, such as the AWS_con_ID. The Postgres hook is also a subclass, namely of the DB API hook. By doing so, it inherits several methods, such as get_records, which executes a given query and returns the results. The return type is a sequence of sequences, more precisely a list of tuples. We then stringify the results and call load_string, which writes encoded data to the given bucket key on AWS S3.